So in this video, I'm going to go over using the information that we copied in Excel for a crank slider linkage and see how we can use that data to create plots and stuff in Excel. Basically, I'm just going to show you how the information from working model for this linkage that we did earlier are copied in Excel, which is the one that we saved in a previous video. And then we're going to use this information to do further post-processing. So when you copy stuff from working model, you have in the order of the measurements that you created in your model. So we had position of the crank, the velocity and the acceleration of the crank. And then we have the position, velocity and acceleration of the coupler. And then I have the position, velocity and acceleration of the slider. So let's create a sheet in here, call it position. And what I want to do is to copy the information for the positions of my links. So I'm gonna first off copy time for 30 seconds that has been saved in here. Then I'm gonna go and grab the rotations of the crank with Control and Shift and down button, and copy this one as well and bring it to here. And go back here. I want the position of the coupler, also only the rotations, and bring them to position. And so let me actually change this to theta 2, and let's change this to theta 3, and let's change this to time. And then I'm going to bring the x component of the positions of the slider, which is this. I'm going to click this, add it to here. So let's call this D. So time, theta 2, theta 3, and D. One thing I want to do is to change the theta 2 and theta 3 into degrees. So I'm gonna write this equation and say this is equal to times 180 divided by pi parentheses. Actually, let me do it here. It's equal to this times 180 divided by pi, and do the same thing for theta 2, and then double click here. Now I want to copy this value to the columns B and C, but there's one thing that we need to also pay attention to, is that when theta 2 reaches 360 degrees, it keeps adding to that. So one thing I want to do also is to subtract 360 degrees from these values. Copy that and paste the value right here. And delete this. Now go back top and copy these columns E and F and save them as values, or paste them as values over here. And then delete the columns E and F. I don't need them. So theta 2 and theta 3 are in degrees, and D is in inches, which is what we want. But there is a problem, because if we look at here, the position of this pin, the pin that connects the crank to the ground, is not at 0, 0. It's at a certain position. So and that is a certain coordinate x and y for that one. So we need to subtract these from the x and y coordinates of the slider to figure out the exact distance between the this pin and the positions of the slider. So if I go here, I see that I have the dimensions or the angle for theta 2, but in sheet 1, if I scroll to the left, and move up, I see X and Y coordinates of the center of mass of the crank. So these are the X and Y coordinates of the center of mass. Let me copy them to here, as I'm going to use them as correction. And this is the angle for that link. So if I subtract these two numbers, and I know that the crank was 4 inches long, if we go back to the picture, the crank was 4 inches long, so the center of mass for a uniform crank is at the center here. So the distance between the two, between this pin and the crank, is 2 inches, half of this. So from here to the center of mass, 2 times cosine of 60 degrees is the x dimension, or the x distance, and 2 times sine of 60 degrees is the y distance. So I can use that to find the coordinates of this pin in working model. Or I can actually get that from working model too, but let's say we don't have access to working model anymore. So this is going to be 2 times cosine of pi over 3, which is 1, and this is 2 times sine of pi over 3. Now if I subtract this from that, this is the coordinate of the pin that connects the crank, the x coordinate of the pin that connects the ground to the crank. And if I subtract this from this value, something happened. Okay, I need to delete that. This is the y coordinate of the pin that connects the crank to the ground. So one thing I can do as a sanity check is to subtract this number. If I add, if I get the distance between these two, actually this one and that one, so if I subtract this and this, should give me 12.684, which is the initial position that we had for the crank, or for the slider. So if I say this is equal to this minus this value, which I'm going to delete, so I'm going to write right here, 29.55, that's the initial position of this slider, and then I can just double click, and that would show me the distance between the pin that connects the crank to the ground and the position of this slider. So I'm going to copy this column and add it as values, or replace it as values over here, and I'm going to remove these values. So I have the positions of the crank in angles, I have the positions in degrees, I have the positions of the coupler in degrees, and I have the position of the slider in inches in the horizontal direction. So I'm gonna select the first 3 columns. I did not hold on the shift button, I have to do it again. So select these 3 headers, control shift down, so I have everything selected. And let's insert a scattered plot. Now it shows us in this plot the position of the crank and the coupler. So I can say the title is position. Let's change these values to other stuff. If I can change a text option to, all right, so these are the calamities that we have to deal with. If I right click here and say select data, and edit this, change the name to the crank, and change the name this one to coupler. So we have these taken care of. Now I can also get the add titles. For the primary one is time and seconds, and the y-axis is angle or angular, let's put angular position, and degrees. And then we can also try to change the plot as we wish, like change the limits of the x-axis and y-axis if we need to. Now we can also try to plot the positions of the this slider. So I can see if I can copy these, Control Shift. It did not select everything that I wanted, so I'm gonna take the time first and then go back to D, Control Shift. So I have the position of the slider also selected, and I'm gonna click on here and create or plot the position of the slider. So now I can see the position of this slider over time. I can change the attributes of my plot as I need it. For example, I can change the axis or horizontal axis to time and in second, and then I can change the slider position to inches. So that is the position of the slider, which seems like harmonic, and then we also have the angular positions of the crank. As you remember, we gave a constant velocity for the crank, so it makes sense that the angular position of the crank is linear. We only changed it from at this point that when it reaches 360 degrees, it resets to 0, and it goes back to like it only fluctuates between 0 and 360 degrees. But as you can see, the coupler doesn't make more rotational or angular positions between 150 and about 190 degrees. It just fluctuates between those two. It's like a harmonic analysis. We can do the same thing for velocity. So I'm going to create a velocity tab. So let's call this velocity. And I want to copy, in this case, actually I can bring the time from here. So I'm going to copy the time. We can bring the angular velocity of the crank. I'm going to copy from here. And let's see if I can copy multiple columns at the same time. I want to copy the angular velocity of the coupler, as well as the x component of velocity of the slider, so this one. So if I copy these 3 columns and put them in here. All right, so this is omega 2, this is omega 3, and this is d dot. So one thing we also see is that the initial velocities are at 0, which is not right, because the initial velocity should be the same as what we gave, and for that I need to find where the crank is back at 60 degrees. So if I move down, I think it's about I moved too far down. I think after it reaches 60 degrees, that's where the motion of our link starts. Oh, I'm looking at the wrong column. Sorry. So if we move forward, we should be able to see that right around here is at line 482 is when the crank reaches back to its initial position of 60 degrees. So if I go to row 482 in the velocity tab, which is right here, I can copy these lines and place them back in here. So these are the angular velocities of the crank and the rocker, as well as the linear velocity of the slider. So like I did for the previous case, I can select these three columns and plot as a scattered plot. So as we expected, the velocity of the crank is constant. In this case, it converted our 15 degrees per second to its radian, and then it also gave us the angular velocity of the coupler, which seems harmonic. And then we can also get the I again forgot to hold on the shift button. So if I go back here, control shift down, go back top and do a control shift down, I have the linear velocity of the slider also selected, insert, scattered, and selection of that one. So we can also see the velocity of the slider. So velocity of the slider, and then we have the angular velocities. So if I go to select data, I can change the first one to crank. I can change the second one to coupler. So we can see the angular velocities as well as the linear velocity of the slider changing in here. And that should tell us, when we want to do analysis, we can make plots like this in Excel very simply and copy them in our presentations or our research papers if we're trying to express how or explain how a system is working. So we can expand these to accelerations. We can do this to more than just angular velocities, angular accelerations. As you can see in this sheet, there's a lot of information output by working models, so we can play with these stuff. But the procedure to do further post-processing of these stuff is the same as I just showed to you in these position and velocity analysis. So we can make plots like that and explain how the mechanism works, and we can explain the dynamics of the mechanism.